Everything you see is an illusion, not in some mystical sense, but in the most literal, physical way possible. That chair you're sitting on, the screen you're reading from, even your own hand, none of it is actually solid. And the particles we've been taught make up everything. They're not really particles at all. What if I told you that reality operates on a level so strange, so fundamentally different from our everyday experience, that even physicists struggle to wrap their minds around it? We're about to explore quantum fields, the invisible fabric underlying absolutely everything in existence. By the time we're done, you'll never look at empty space the same way again. Here's the setup. For centuries, we thought of particles as tiny billiard balls, indivisible chunks of matter bouncing around through empty space. An electron was a thing, a photon was a thing, a quark was a thing. Simple, concrete, wrong. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. The reality is far more beautiful and bizarre. What we call particles are actually ripples in invisible fields that permeate every cubic centimeter of the universe. These aren't fields in the way a farmer has a field. They're mathematical entities existing at every point in space and time simultaneously. The electron field stretches across the entire cosmos. So does the quark field, the photon field, the Higgs field. Dozens of these fields layered on top of each other, vibrating and interacting in ways that create everything you've ever seen or touched. When you observe an electron, you're not seeing a little ball of matter. You're seeing a localized excitation in the electron field, a wave, a disturbance. Think of it like pressing down on a mattress. You create an indentation, a localized deformation. That indentation is what we call a particle. Except this mattress stretches across all of reality, and the indentation can move, interact with other indentations, even disappear entirely. Now, this gets weird fast, because unlike a real mattress where you can press down any amount you want, quantum fields only allow excitations in specific discrete amounts. You can have 1 electron's worth of excitation, 2 electrons, 3, but never 1.5 electrons. The field is quantized, hence the term quantum field. Energy comes in packets, and those packets are what we've been calling particles. Let's pause here because this is where most explanations go off the rails. People hear field and imagine something flowing or waving smoothly through space. That's not quite right. Quantum fields don't flow. They vibrate, they oscillate, and they do so in discrete, countable units. The field itself exists everywhere, always. What changes is the pattern of excitation. Consider the ocean. Water molecules fill the entire body. That's your field. Waves are excitations moving through it. But here's where the analogy breaks down. Ocean waves can have any height, any energy. Quantum field excitations can't. They're digital, not analog. On or off, 1 quantum or 0 quanta. This discreteness is what makes the quantum world so profoundly different from our everyday experience. So what does the vacuum state look like? You might imagine empty space as just nothing, a void. But in quantum field theory, the vacuum is the state where all fields exist at their lowest possible energy, not 0 energy. That would violate the uncertainty principle. Instead, these fields are constantly fluctuating, bubbling with virtual particles popping in and out of existence so quickly, We can't directly observe them. These aren't metaphors. Virtual particles have real, measurable effects. Put two metal plates close together in a vacuum, and they'll experience an attractive force, the Casimir effect. Why? Because the space between the plates restricts which vacuum fluctuations can exist there, creating a pressure difference. The vacuum is pushing the plates together. Empty space has structure, has energy, has consequences. The electron field demonstrates this perfectly. It exists at every point in the universe, and at each point it has a complex mathematical value. When we create an electron in a particle accelerator, we're not conjuring matter from nothing. We're pumping energy into the electron field until it reaches an excited state at that location. The excitation has a specific energy. The electron's mass via E equals mc squared plus whatever kinetic energy we give it. It carries charge, spin, and other quantum properties. But here's what really bends your mind. That electron isn't moving through space like a marble rolling across a table. The excitation in the field is propagating. The field itself is everywhere, but the pattern of high excitation, what we call the electron, moves from place to place. It's less like a ball rolling and more like a wave traveling across water. Except remember, it's a quantized wave, an indivisible packet of energy. The electromagnetic field bridges our classical intuitions with quantum reality. We're familiar with electromagnetic fields, from magnets, radio waves, light. Maxwell's equations describe them beautifully. But when you apply quantum mechanics to the electromagnetic field, something remarkable emerges. Light comes in discrete packets. Photons. Each photon represents one quantum of excitation in the electromagnetic field. Its energy depends on frequency. Higher frequency means more energy per photon. But unlike electrons, photons are bosons. They don't obey the Pauli exclusion principle. You can pack unlimited numbers of photons into the same quantum state, which is why we can create intense laser beams with billions of photons, all synchronized, all coherent. This is where forces get interesting. When two electrons repel each other, quantum field theory says they're exchanging virtual photons. These are brief excitations in the electromagnetic field that pop into existence, carry momentum from one electron to the other, then vanish. The virtual photon borrows energy from the vacuum, permitted by the uncertainty principle for incredibly short times, and this exchange creates what we experience as the electromagnetic force. You might ask, how can particles that don't really exist carry real forces? Because virtual particles aren't particles in the traditional sense. They're mathematical terms in a calculation. They represent the ways quantum fields can interact. When we draw Feynman diagrams showing virtual photons connecting two electrons, we're creating a visual representation of a mathematical expression. Each diagram corresponds to a specific calculation that predicts the probability of the interaction. Now we need to talk about the Higgs field, because it's fundamentally different from every other field we've discussed. Most quantum fields have a vacuum expectation value of 0. In their ground state, the field averages to nothing. The Higgs field doesn't. It has a constant, non-zero value throughout all of space. Always. Everywhere. This uniform background of Higgs field is what gives particles mass. Particles interact with this field as they move through space. Some particles interact strongly. They experience significant resistance, manifest as large mass. Others interact weakly, resulting in small mass. Photons don't interact with the Higgs field at all, which is why they're massless. Imagine swimming through a pool. Now imagine swimming through honey. The honey provides more resistance, making it harder to accelerate. That resistance, that inertia, is analogous to mass. The Higgs field is like honey filling all of space, and different particles experience different levels of viscosity depending on how they couple to the field. The Higgs boson, the particle discovered at CERN in 2012, is an excitation of the Higgs field above its non-zero background value. It's not the field itself, but a ripple on top of the field's constant presence. Creating a Higgs boson requires enormous energy because you're not starting from zero. You're pushing the field even higher above its already elevated baseline. That's why the Large Hadron Collider needed such extreme energies to produce it. But quantum fields get even stranger when we look at quarks. There are 6 types of quark fields, and each quark comes in 3 colors. Not actual colors, but a property called color charge. The strong nuclear force binding quarks together is mediated by gluon fields. 8 different types of gluons, each carrying combinations of color charge. Here's where things diverge dramatically from electromagnetism. Photons don't carry electric charge, so they don't interact with themselves. Gluons carry color charge, so they interact with other gluons. This self-interaction creates a phenomenon called confinement. You can never isolate a single quark. Try to pull quarks apart, and the strong force actually gets stronger with distance, like stretching a rubber band. Eventually, you pump in enough energy to create new quark-antiquark pairs, and you end up with multiple bound states instead of free quarks. Quantum chromodynamics, the theory of quark and gluon fields, exhibits asymptotic freedom. At extremely high energies, when quarks are smashed very close together, they interact weakly. This makes calculations possible for high-energy collisions. But at low energies, where quarks are bound inside protons and neutrons, the interactions become so strong that calculations require supercomputers running for months. We can simulate the behavior, but the math is brutally complex. All of this, electrons, photons, quarks, gluons, the Higgs boson, fits together in what we call the standard model of particle physics. It's a specific quantum field theory with a particular mathematical structure, described by the gauge symmetry group SU 3 times SU 2 times U1. Those symbols encode the symmetries that dictate how the fields interact. The standard model has been absurdly successful. It predicted the existence of quarks before we found them, predicted the W and Z bosons, predicted the Higgs. Calculations using quantum electrodynamics match experimental measurements to 12 decimal places. 12. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. Yet it's incomplete. The standard model doesn't include gravity, doesn't explain dark matter or dark energy, doesn't tell us why there are 3 generations of fermions, or why particles have the specific masses they do. About 19 free parameters, numbers we have to measure experimentally rather than derive from the theory. These are clues that the standard model, for all its success, is not the final answer. What makes quantum fields truly fundamental is how they unify quantum mechanics with special relativity. Earlier quantum theories treated time as a parameter and position as an operator, creating an asymmetry. Special relativity demands space and time be treated equally. Quantum field theory accomplishes this by making the fields themselves the fundamental objects defined at each point in space-time. This framework naturally accommodates particle creation and annihilation. When you try to localize a particle to a region smaller than its Compton wavelength, you supply enough energy to potentially create particle-antiparticle pairs. The theory must allow particle number to change, and it does, elegantly. The Dirac equation for electrons automatically predicts positrons. Every fermion field has a corresponding antiparticle field built right into the mathematics. The spin statistics theorem emerges from this framework too. It explains why fermions obey the Pauli exclusion principle while bosons don't. The theorem is a consequence of demanding that quantum field theory respect both quantum mechanics and special relativity while preserving causality, ensuring signals can't travel faster than light. These requirements force fermions and bosons to behave differently. Even the vacuum isn't empty in this picture. Heisenberg's uncertainty principle means quantum fields can't have precisely zero value with zero uncertainty. Fields constantly fluctuate around their average values. These vacuum fluctuations are real. They contribute to the Lamb shift in hydrogen atoms. They affect the magnetic moment of electrons. Virtual particle-antiparticle pairs pop into existence briefly, live on borrowed energy, then annihilate. Most of a proton's mass comes from these fluctuations. The up and down quarks inside a proton have tiny masses, a few mega-electronvolts each. But the proton weighs 938 mega-electronvolts. Where does that extra mass come from? Virtual quarks and gluons. The kinetic energy of these quantum field fluctuations, confined within the proton, manifests as mass. The proton is essentially a roiling sea of quantum field excitations, barely contained by the strong force. This is what reality actually is at its deepest level. Not particles bouncing through empty void, but fields, invisible, intangible mathematical entities, vibrating in patterns that create everything we see. The solidity of matter is an illusion created by electromagnetic field interactions. The distinctness of objects is an illusion created by how excitations localize in space. Even empty space is an illusion, filled with fields fluctuating at every point. Understanding quantum fields requires abandoning nearly every intuition we've built up about how the world works. But that's where we're headed. We're going to explore how these fields actually behave, how physicists discovered them, and what it means that reality operates on such a strange foundation. The mathematics gets intense, the concepts get slippery, but the payoff is understanding existence at its most fundamental level. Because once you see reality as quantum fields, you can't unsee it. The chair beneath you becomes a pattern of electron field excitations, interacting electromagnetically with the electron field excitations in your body. Light becomes ripples in the photon field entering your eye and exciting the electron field in your retina. You become a temporary, localized pattern of multiple field excitations, held together by force-carrying field excitations, all vibrating in concert. That's the world we actually inhabit. Now let's see how we figured this out, and what it really means when we say particles don't exist. Only fields do. The discovery of quantum fields wasn't some sudden revelation. It was messy, frustrating, and took decades of brilliant minds wrestling with mathematical nightmares that seemed unsolvable. Let's go back to the 1920s. Quantum mechanics had just been born, and physicists were riding high on success. They could predict atomic spectra, explain chemical bonds, describe radioactivity. But there was a problem lurking beneath the surface. Paul Dirac saw it first. He was trying to write an equation for the electron that respected both quantum mechanics and Einstein's special relativity. The equation he found in 1928 was beautiful. It predicted electron spin automatically, explained magnetic properties perfectly. But it also predicted something nobody expected: negative energy solutions. The equation allowed electrons with negative total energy. This made no physical sense. If negative energy states existed, every electron in the universe should cascade down into them, releasing infinite energy and destroying all matter. Obviously, this wasn't happening. Dirac's solution was radical. He proposed that all the negative energy states were already filled with electrons, creating what he called the Dirac Sea, an invisible ocean of negative energy electrons pervading all space. A hole in this sea, a missing negative energy electron, would appear as a positive energy particle with opposite charge. He'd predicted antimatter. 4 years later, Carl Anderson discovered the positron in cosmic rays, and Dirac's seemingly crazy idea became physical reality. But the Dirac Sea picture was clunky and philosophically troubling. It required an infinite number of invisible electrons filling the universe just to make the math work. There had to be a better way to think about this. The better way was quantum field theory. Instead of treating the electron as a particle, treat the electron field as fundamental. Positive energy solutions correspond to particle excitations. Negative energy solutions correspond to antiparticle excitations. No infinite sea needed. Just one field with two types of excitations. Elegant. But implementing this idea mathematically proved nightmarish. When physicists tried calculating anything beyond the simplest processes, they hit a wall. Infinities. Everywhere. Calculate the energy of an electron, including its own electromagnetic field. Infinite. Calculate the probability of two electrons scattering. Infinite. Calculate how a magnetic field affects an electron. Infinite. These weren't just large numbers. They were actual mathematical infinities that made the theory useless for predictions. Physicists spent nearly 2 decades trying to fix this. The breakthrough came after World War II. A conference at Shelter Island in 1947 brought together the brightest minds in physics. New experimental results showed tiny discrepancies from Dirac's predictions. The Lamb shift in hydrogen atoms, anomalies in the electron's magnetic moment. These weren't errors, they were real physical effects. Hans Bethe made the first move, calculating the Lamb shift by introducing a cutoff, essentially ignoring contributions from extremely high energies. It was crude, but it worked. The calculation matched experiment. Then, Julian Schwinger, Richard Feynman, and Shinichiro Tominaga independently developed the full theory of renormalization. The key insight: the parameters we put into our equations aren't the quantities we measure. When you write down the bare mass of an electron in your equations, that's not the mass you measure in a lab. The measured mass includes all the effects of the electron interacting with quantum fields, virtual photons being emitted and absorbed, virtual electron-positron pairs appearing and disappearing. These interactions contribute to the electron's effective mass. The infinities in the calculations were telling us something profound. We can't separate a particle from the quantum fields it interacts with. The bare mass might be infinite, but it's unobservable. What we measure is always the renormalized mass, bare mass, plus all quantum corrections. By carefully redefining our parameters to absorb the infinities, we could make finite predictions. And these predictions were stunningly accurate. Feynman's contribution went beyond mathematics. He invented a visual language for quantum field theory, Feynman diagrams, simple pictures where lines represent particles and vertices represent interactions. An electron moving through space, draw a line. An electron emitting a photon, draw two lines meeting at a point. An electron and positron annihilating into photons, lines coming together and new lines emerging. Each diagram corresponds to a mathematical expression. More complex diagrams with more virtual particles represent smaller corrections. You can calculate the probability of any process by drawing all possible diagrams and adding up their contributions. This visual approach revolutionized physics. Suddenly, quantum field theory became accessible. You could see what was happening, organize calculations systematically, even guess at new effects by drawing diagrams nobody had calculated yet. The success of quantum electrodynamics was extraordinary. By the 1950s, physicists could predict the electron's magnetic moment to 8 decimal places. Experiments matched theory perfectly. QED became the most precisely tested theory in all of science. But there were other forces to understand. The weak nuclear force responsible for radioactivity, the strong force holding atomic nuclei together, could they also be described by quantum field theories? The weak force proved particularly troublesome. It seemed fundamentally different from electromagnetism. It could change one particle type into another, a neutron into a proton, a muon into an electron. It violated symmetries that electromagnetism respected, and calculations gave infinities that couldn't be renormalized using the techniques that worked for QED. Sheldon Glashow, Abdus Salam, and Steven Weinberg solved the puzzle in the 1960s by unifying the weak force with electromagnetism. At high energies, they argued, these weren't separate forces, but different aspects of a single electroweak interaction. The key was spontaneous symmetry breaking through the Higgs mechanism. The universe's ground state, the vacuum, doesn't respect the symmetries of the underlying laws. The Higgs field has a non-zero value everywhere, hiding the fundamental symmetry and making the forces appear different at low energies. This gave mass to the W and Z bosons that carry the weak force while leaving the photon massless. It made the theory renormalizable, and it predicted the existence of a new particle, the Higgs boson. The strong force required different techniques. Quarks had been proposed to explain patterns in particle physics, but nobody had ever seen an isolated quark. They were always bound inside protons, neutrons, or other particles. The theory that emerged, quantum chromodynamics, explained this confinement. Quarks carry color charge coming in 3 varieties. The strong force is mediated by gluons, which, unlike photons, carry charge themselves. This self-interaction makes the strong force strengthen with distance. Try to pull quarks apart, and the force grows stronger, like stretching a rubber band. Eventually, you put in enough energy to create new quark-antiquark pairs from the vacuum. You never liberate a single quark. You just make more bound states. QCD also exhibited asymptotic freedom. At extremely high energies, when quarks are crushed close together, the strong force becomes weak. This let physicists do calculations for high-energy collisions, even though low-energy strong force calculations remained impossibly difficult. David Gross, Frank Wilczek, and David Politzer discovered asymptotic freedom in 1973. earning the Nobel Prize 30 years later. By the mid-1970s, these pieces came together into the Standard Model. One unified quantum field theory describing 3 of the 4 fundamental forces: 12 matter particles, 6 quarks, and 6 leptons in 3 generations, 4 force-carrying particles for electromagnetism, 3 for the weak force, 8 for the strong force, plus the Higgs boson. The Standard Model made specific predictions. The charm quark would exist with particular properties. The bottom and top quarks would exist at specific masses. The W and Z bosons would have precise masses and interaction strengths. The Higgs boson would exist with calculable decay modes. Over the following decades, every prediction came true. The charm quark appeared in 1974, bottom in 1977, top in 1995. The W and Z bosons were discovered in 1983 with exactly the predicted properties. The Higgs boson finally appeared in 2012 at the Large Hadron Collider. The Standard Model became the most successful theory in physics. Calculations match experiments to absurd precision. The electron magnetic moment agrees with QED predictions to better than 1 part in a trillion. No experiment has ever found a confirmed deviation from Standard Model predictions. And yet, we know it's incomplete. The Standard Model doesn't include gravity. General relativity describes gravity beautifully at large scales, but we don't have a quantum field theory of gravity. When we try to quantize gravity, we get infinities that can't be renormalized. The theory breaks down. The Standard Model doesn't explain dark matter, which makes up 85% of matter in the universe. Dark matter doesn't fit into any of the particle categories in the model. It doesn't explain dark energy driving cosmic acceleration. The vacuum energy predicted by quantum field theory is wrong by 120 orders of magnitude, the worst prediction in physics history. It doesn't explain why matter vastly outnumbers antimatter in our universe. The Standard Model allows some matter-antimatter asymmetry, but not nearly enough to explain what we observe. It doesn't explain neutrino masses. The original Standard Model assumed neutrinos were massless, but experiments proved they have tiny masses. We can modify the theory to accommodate this, but we don't know why neutrino masses are so incredibly small. It contains 19 free parameters, masses, coupling strengths, mixing angles, whose values must be measured experimentally. The theory can't predict them. Why does the electron have the mass it does? Why is the fine structure constant approximately 1/137? The Standard Model offers no answers. These gaps tell us the Standard Model isn't final. It's an effective theory, valid at accessible energies, but incomplete. There must be deeper physics waiting to be discovered. String theory, supersymmetry, extra dimensions. Theoretical physicists have proposed many extensions beyond the Standard Model. But without experimental evidence, we're stumbling in the dark. What we do know is that quantum fields are real. They're not just mathematical tools, but fundamental features of reality. Every experiment confirms this. The Casimir effect measures vacuum fluctuations directly. Particle accelerators create and destroy field excitations routinely. The Higgs discovery confirmed that fields with non-zero vacuum values exist throughout space. Understanding how we discovered all this, the decades of struggle, the brilliant insights, the experimental confirmations, helps us grasp what quantum fields actually are. They're not abstract concepts divorced from physical reality. They're the foundation that reality builds upon. But knowing the history only takes us so far. To really understand quantum fields, we need to explore how they actually behave, how excitations propagate through them, how fields interact with each other, how the mathematics translates into physical phenomena we can observe and measure. That's where we're headed next, into the mechanics of quantum fields themselves, where the abstract becomes concrete and the mathematical becomes physical. The quantum vacuum isn't empty. That's the first thing that shatters our classical intuitions. Picture absolute nothingness. No particles, no energy, perfect zero. Quantum field theory says that's impossible. The vacuum state, the lowest energy configuration of a quantum field, still seethes with activity. Fields fluctuate constantly, never sitting perfectly still. This isn't philosophical hand-waving. It's measurable physics with concrete experimental consequences. Heisenberg's uncertainty principle applies to fields just as it does to particles. A field can't have precisely zero value with zero uncertainty simultaneously. The field must fluctuate, jittering around an average value of zero. These vacuum fluctuations occur at every point in space, at every frequency, creating what physicists call zero-point energy. The quantum vacuum is a roiling sea of activity at scales too small and too brief for us to observe directly, but substantial enough to affect everything we can measure. The Casimir effect provides direct evidence. Take two uncharged metal plates and place them extremely close together in a vacuum. Classical physics predicts nothing should happen. There's no charge, no magnetic field, no apparent force between them. But quantum field theory predicts an attractive force, and experiments confirm it precisely. The vacuum between the plates differs from the vacuum outside because the plates restrict which wavelengths of field fluctuations can exist in the gap. Long wavelength fluctuations can't fit between closely spaced plates. This creates an imbalance in vacuum energy, more fluctuations pushing from outside than from inside, resulting in a measurable force pulling the plates together. Hendrik Casimir predicted this effect in 1948, based purely on quantum field theory calculations. The first precise experimental confirmation came in 1997, with measurements matching theoretical predictions to better than 1% accuracy. That metal plates in apparent vacuum experience force purely from quantum fluctuations isn't speculation, it's tested reality. The Lamb shift provides another verification. Hydrogen's electron energy levels, calculated using Dirac's equation, should have certain specific values, but precise measurements revealed tiny deviations that Dirac's equation couldn't explain. These shifts emerge naturally when you account for vacuum fluctuations in the electromagnetic field. The electron constantly emits and reabsorbs virtual photons, brief excitations in the electromagnetic field permitted by uncertainty. These interactions modify the electron's energy levels in ways that match experimental observations with extraordinary precision. Virtual particles represent perhaps the strangest consequence of vacuum fluctuations. Particle-antiparticle pairs spontaneously appear from the vacuum, exist briefly, then annihilate. An electron-positron pair can materialize from nothing, live on borrowed energy for a time permitted by the uncertainty principle, then vanish. The higher the energy borrowed, the shorter the permitted lifetime. Virtual particles with large energy imbalances must disappear almost instantly. Those borrowing less energy can persist slightly longer. These virtual particles aren't hypothetical constructs. They contribute to measurable physical quantities. The electron's magnetic moment, how strongly it responds to magnetic fields, differs slightly from predictions that ignore virtual particles. When you account for virtual photons, virtual electron-positron pairs, and more exotic virtual processes, the calculated value matches experimental measurements to 12 decimal places. That's agreement to better than 1 part in a trillion. Virtual particle effects are real. Inside a proton, virtual quarks and gluons dominate. The mass of a proton comes almost entirely from the kinetic energy of these virtual particles constantly appearing and disappearing. The actual rest masses of the up and down quarks inside account for roughly 1% of the proton's mass. The other 99% is pure energy from the strong force field and its quantum fluctuations. What we perceive as solid matter is mostly the frantic activity of quantum fields in their lowest energy state. But here's what trips people up. Virtual particles aren't tiny objects popping into existence like microscopic firecrackers. They're quantum field fluctuations, mathematical terms in calculations that happen to correspond to particle-like behavior. When we say a virtual photon is exchanged between two electrons, we're describing a process where the electromagnetic field fluctuates in a way that transfers momentum and energy. The photon language is convenient shorthand for field dynamics, not a description of little light particles briefly materializing. Field propagation reveals how excitations move through quantum fields. When you create a particle, say an electron at a specific location, you've excited the electron field there. That excitation doesn't stay frozen in place. It propagates through the field according to specific mathematical rules encoded in the field's equations of motion. The electron field's excitation spreads outward, carrying energy and momentum, behaving like what we call a moving particle. But the propagation isn't simple. The excitation you created can interact with other fields. The electron field couples to the electromagnetic field, meaning an electron excitation can emit or absorb photons. It couples to the weak field, allowing certain decay processes. These interactions modify how the excitation propagates. A free electron is never truly free. It's constantly emitting and reabsorbing virtual photons, surrounded by a cloud of field fluctuations that dress the bare excitation with additional structure. The propagator in quantum field theory encodes this behavior mathematically. It describes the probability amplitude for an excitation to travel from one space-time point to another. For a photon, the propagator falls off as 1 over the distance squared, reflecting the long-range nature of electromagnetism. For massive particles, the propagator includes exponential suppression at distances larger than the particle's Compton wavelength. Short-range forces like the weak interaction have massive force carriers, making their propagators drop off rapidly with distance. Field interactions happen through coupling terms in the Lagrangian, the mathematical function that encodes all the field's dynamics. When two fields have a coupling term, excitations in one field can create or destroy excitations in the other. The electron field couples to the electromagnetic field through a term that looks like the electron field times the electromagnetic field times the electron field again. This coupling allows electrons to emit or absorb photons, creating all electromagnetic interactions. The strength of the coupling determines how frequently interactions occur. Electromagnetic coupling is characterized by the fine structure constant, approximately 1/137. This number appears throughout QED calculations, determining interaction probabilities. Weak coupling is much smaller, making weak interactions rare despite being fundamental. Strong coupling is, unsurprisingly, strong, but its strength depends on energy scale in ways that make QCD calculations fiendishly difficult at low energies. Feynman diagrams translate these couplings into visual representations of processes. Each line represents a field's propagation. Each vertex where lines meet represents a coupling term, an interaction allowed by the theory's mathematical structure. You can write down every possible Feynman diagram for a process, calculate the corresponding mathematical expression for each diagram, sum them all, and obtain a prediction for the process probability. Simple diagrams contribute most. An electron scattering off another electron can happen through a single virtual photon exchange. One diagram with two vertices. But it can also happen through two virtual photons being exchanged, or a virtual photon splitting into a virtual electron-positron pair, or countless more complex possibilities. Each additional vertex multiplies by the coupling constant, suppressing the contribution. For electromagnetism, each extra vertex multiplies by roughly 1/137, making higher-order corrections progressively smaller. This perturbative approach works beautifully for electromagnetism and the weak force where coupling constants are small. You calculate the first few diagrams, get a good approximation, then add more diagrams for better precision. QED calculations summing hundreds of Feynman diagrams match experiments to absurd precision. But for the strong force at low energies, the coupling constant isn't small. Perturbation theory breaks down. You can't trust calculations based on adding up Feynman diagrams because they don't converge to a sensible answer. Lattice QCD solves this by discretizing spacetime. Instead of treating spacetime as continuous, you place it on a grid, a lattice of points separated by tiny distances. Quantum fields live on this lattice, and you simulate their behavior using supercomputers. This numerical approach doesn't rely on perturbation theory. It can handle strong coupling by directly computing field configurations and their probabilities. Modern lattice QCD calculations predict proton masses, quark binding energies, and other quantities from first principles, matching experimental measurements when sufficient computational power is applied. Field oscillations behave like harmonic oscillators, masses on springs vibrating at specific frequencies. Quantum mechanics tells us harmonic oscillators have discrete energy levels separated by steps of h-bar omega, where omega is the oscillation frequency. The lowest energy level isn't zero, it's 1/2 h-bar omega, the 0-point energy. A quantum field is like an infinite collection of harmonic oscillators, one at each point in space, each frequency contributing its 0-point energy. Summing all these contributions gives infinite vacuum energy, one of the most vexing problems in theoretical physics. Renormalization handles infinities by recognizing that bare parameters in our theories aren't directly observable. What we measure are effective parameters that include all quantum corrections. The electron's bare mass might be infinite, but its observed mass is finite, because infinite corrections from field interactions exactly cancel the bare infinity. This systematic subtraction procedure, renormalization, converts infinite calculations into finite predictions that match experiments. Not all theories are renormalizable. Quantum field theories must have specific mathematical structures to allow consistent renormalization. The Standard Model possesses this structure, which is why it makes successful predictions. Theories of quantum gravity generally aren't renormalizable in the standard sense, creating infinities we can't systematically remove. This suggests quantum gravity requires different mathematical frameworks, perhaps string theory, loop quantum gravity, or something not yet imagined. Effective field theory embraces incompleteness. We don't need a complete theory valid at all energy scales to make predictions at accessible energies. The effective theory captures relevant physics up to some energy cutoff, parameterizing our ignorance of higher energy physics through a finite set of constants determined by experiment. As long as we're asking questions below the cutoff energy, effective field theory works perfectly. This framework explains why we can do physics at all without knowing the ultimate theory of everything. Symmetries dictate interactions. Gauge symmetry, the freedom to make certain mathematical transformations without changing physical predictions, requires force carrier particles to exist. Local U1 symmetry of the electron field's phase demands the existence of the photon and determines how electrons couple to electromagnetic fields. The photon is massless because U1 gauge symmetry forbids a mass term. The electromagnetic interaction's entire structure emerges from insisting the theory remain invariant under phase rotations that can differ at each spacetime point. SU2 weak symmetry requires W and Z bosons. SU3 color symmetry requires 8 gluons. The Standard Model's gauge group, SU 3 times SU 2 times U1, determines all force carriers and their interactions before we've measured anything experimentally. Symmetry principles constrain theories so severely that knowing the symmetry group almost writes the theory for you. Spontaneous symmetry breaking occurs when a theory's laws possess symmetry, but the ground state doesn't. The Higgs field's non-zero vacuum value breaks electroweak symmetry, giving masses to W and Z bosons while leaving the photon massless. Below the energy scale of electroweak symmetry breaking, electromagnetism and weak force appear distinct. Above that scale, they unify into a single electroweak interaction. The universe transitioned through this symmetry-breaking phase transition a fraction of a second after the Big Bang, fundamentally changing which particles could exist and how they interact. Conservation laws follow from symmetries through Noether's theorem. Time translation symmetry gives energy conservation. Space translation symmetry gives momentum conservation. Rotational symmetry gives angular momentum conservation. Gauge symmetries give conserved charges, electric charge from U1 symmetry, weak isospin from SU2, color charge from SU3. Every conservation law we observe traces back to an underlying symmetry. Beta decay illustrates these principles in action. A neutron transforms into a proton, electron, and electron antineutrino. In field language, a down quark field excitation becomes an up quark field excitation by emitting a W boson field excitation. The W boson is virtual, existing briefly with insufficient energy to be a real W boson. It decays into electron and antineutrino field excitations. The process conserves energy, momentum, electric charge, and lepton number, all consequences of underlying symmetries. The weak force changes quark flavors, transforming down quarks into up quarks or strange into charm. This flavor-changing ability makes the weak force unique. Electromagnetism preserves quark type. The strong force preserves it. Only the weak force allows one quark flavor to become another, enabling processes like beta decay that transform one element into another. Without weak interactions, stars couldn't fuse hydrogen into helium. The universe would be radically different. Quantum field theory's success is staggering. Predictions match experiments to precisions unmatched in any other science. Yet mysteries remain. Dark matter doesn't fit into standard model fields. Dark energy suggests vacuum energy calculations are wrong by 120 orders of magnitude. Matter-antimatter asymmetry exceeds what standard model physics allows. Neutrino masses require extensions to the original framework. Gravity remains outside the quantum field theory formalism. These gaps point toward physics beyond what we currently understand. New fields, new symmetries, new principles waiting to be discovered. The standard model is an effective theory, valid in its domain, but incomplete. What lies beyond might be supersymmetry, extra dimensions, or something entirely unexpected. But whatever comes next must reproduce quantum field theory's extraordinary successes while resolving its remaining puzzles. Virtual particles live in a strange twilight zone between existence and non-existence. They're not particles in any conventional sense. They're mathematical expressions representing quantum field fluctuations that violate energy conservation for timeframes so brief that uncertainty shields them from detection. When an electron and electrons scatter off each other, the calculation requires summing over every possible virtual photon they might exchange. Infinite possibilities. Each contributes a tiny amplitude to the final probability. The photon carrying zero energy. The photon carrying enormous energy. Photons at every conceivable momentum. All of them factor into what actually happens. Here's what makes this genuinely strange. The virtual photon exchange between two electrons doesn't satisfy E squared equals PC squared plus MC squared squared. Real photons obey this relation exactly. Virtual photons don't. They're off-shell, borrowing energy from the vacuum through quantum uncertainty's loophole. The more energy borrowed, the briefer their existence. A virtual photon carrying enormous energy must be reabsorbed almost instantaneously. One carrying little energy can persist longer, but none are real in the sense that you could detect them directly. The Lamb shift proves virtual particles have measurable consequences. In hydrogen atoms, the electron's energy levels show tiny splittings that Dirac's equation doesn't predict. These splittings arise from virtual photons being emitted and reabsorbed by the electron. The electron interacts with its own electromagnetic field's quantum fluctuations. Virtual photons pop out, exist briefly, get reabsorbed. This constant jittering modifies the electron's energy ever so slightly. Measurements match theoretical predictions to extraordinary precision. Your body contains virtual particles right now. Between the quarks inside every proton and neutron, virtual gluons constantly appear and vanish. Virtual quark-antiquark pairs flash in and out of existence. This seething quantum foam contributes most of a proton's mass. The up and down quarks themselves account for roughly 1%. The other 99% comes from the kinetic energy of these virtual particles dancing through the strong force field. Mass emerges from pure energy. Einstein's equation made manifest in the quantum realm. Casimir effect demonstrates vacuum fluctuations more directly. Place two uncharged metal plates extremely close together in a vacuum. They attract each other, not through gravity or electromagnetism in any classical sense, but through quantum field fluctuations. The vacuum between the plates restricts which wavelengths of electromagnetic field fluctuations can exist there. Outside the plates, all wavelengths are possible. This creates an imbalance in vacuum energy density, pushing the plates together. Experimentalists have measured this force. It matches quantum field theory's predictions. Path integrals offer a radically different way of thinking about quantum field theory. Instead of particles following definite trajectories, Feynman's formulation says they take every possible path simultaneously. A photon traveling from point A to point B doesn't follow one route. It follows all routes. Straight lines, wild spirals, detours to distant galaxies and back. Each path contributes an amplitude to the final probability. Paths close to the classical trajectory contribute coherently, reinforcing each other. Wildly different paths tend to cancel out through quantum interference, but they all count. This path integral approach extends to fields. Rather than describing how field values evolve in time through equations of motion, you sum over all possible field configurations. Every conceivable way the field could arrange itself throughout space-time contributes to the calculation. Field values oscillating rapidly. Field values changing gradually. Configurations where the electron field is excited here but not there. Configurations where it's excited everywhere. The sum over these infinite possibilities determines what we observe. Mathematically, this seems insane. How do you sum over infinitely many field configurations? The answer involves sophisticated mathematical techniques, functional integrals, generating functionals, clever tricks for handling infinities. But conceptually, it reveals something profound. Quantum field theory doesn't describe what fields do. It describes what they could do, weighted by quantum probability. Reality emerges from the superposition of all possibilities. Gauge invariance becomes more transparent in the path integral formulation. When you sum over field configurations, many of them are physically equivalent. They differ only by a gauge transformation. These redundant configurations shouldn't contribute multiple times to physical predictions. Properly accounting for gauge invariance requires carefully defining which field configurations count as genuinely different. This leads to the Faddeev-Popov procedure, introducing ghost fields that aren't real particles but mathematical devices, ensuring gauge symmetry is maintained throughout calculations. Effective field theory represents a philosophical shift in how physicists approach quantum field theory. Rather than seeking one ultimate theory valid at all energy scales, effective field theory acknowledges that different physics dominates at different scales. At energies accessible to current experiments, we don't need to know the complete structure of reality at Planck scale energies. We can construct an effective theory valid in our energy regime, making predictions without solving everything. Consider the Standard Model itself. It's an effective field theory, valid up to some energy scale where new physics must enter. Below that scale, Standard Model calculations work beautifully. Above it, new fields, new particles, new interactions might appear. The effective theory framework lets us make precise predictions while remaining agnostic about ultimate foundations. You include all interactions allowed by your symmetries, organized by their strength at relevant energy scales. Low energy physics depends primarily on the most important terms. Higher order corrections are suppressed by powers of energy over the scale where new physics enters. This resolves renormalization's conceptual difficulties. Those troublesome infinities arose from integrating over arbitrarily high energies where we shouldn't trust our theory anyway. Effective field theory recognizes this explicitly. You cut off the integration at some energy scale, include only the physics you can reliably describe, and parameterize your ignorance about high-energy physics through measurable coefficients. The theory makes definite predictions for accessible energies without claiming to describe physics at all scales. Lattice quantum field theory takes a different approach to taming infinities. Instead of continuous space-time, imagine space and time as a discrete lattice, a grid of points. Fields live on lattice sites. Particles hop between sites. This discretization automatically provides a cutoff, eliminating ultraviolet divergences from arbitrarily short distances. You can then perform calculations using Monte Carlo simulations on supercomputers, numerically evaluating the path integral over field configurations. Lattice QCD has been particularly successful. The strong forces complications make analytical calculations nearly impossible at low energies where quarks are tightly bound. But on a lattice, you can simulate quark and gluon field configurations directly. Start with a random configuration. Evolve it according to QCD's rules. Generate many configurations. Average over them. This produces predictions for hadron masses, decay constants, scattering amplitudes, all quantities that emerge from QCD but are too complex to calculate analytically. Modern lattice QCD simulations use lattices with billions of sites, requiring massive computational resources. But they've achieved remarkable precision. Calculated proton and neutron masses match experimental values to within a few percent. Predictions for processes involving quarks and gluons at low energies agree with measurements. This validates QCD as the correct theory of the strong force and demonstrates that quantum field theory can make quantitative predictions even when perturbation theory fails. Anomalies reveal subtle mathematical constraints on quantum field theories. An anomaly occurs when a symmetry of the classical theory doesn't survive quantization. The most famous example is the chiral anomaly in QED. Classically, you might expect left-handed and right-handed electrons to be conserved separately. But quantum corrections break this conservation. Triangle diagrams involving three currents generate an anomaly that destroys the classical symmetry. This might sound like a problem, but anomalies actually constrain theories powerfully. For the standard model to be mathematically consistent, certain anomalies must cancel. The charges and quantum numbers of quarks and leptons are arranged such that all dangerous anomalies vanish. If you try to build a theory with different particle content, you'd likely get anomalies that render it inconsistent. The fact that the standard model is anomaly-free isn't coincidence. It's a necessary condition for the theory to work. Instantons represent non-perturbative phenomena in quantum field theory, effects that don't show up in any finite order of perturbation theory. They're classical field configurations that minimize the action, but aren't trivial vacuum. In QCD, instantons correspond to tunneling events between different vacuum states. These configurations are localized in spacetime, existing for a brief moment before disappearing. They contribute to the path integral, but can't be captured by Feynman diagrams. Instantons help explain the strong CP problem, why QCD doesn't violate charge parity symmetry, despite having terms in its equations that could. The resolution might involve the axion, a hypothetical particle that would cancel the CP violating effects. Axions would be extremely light, weakly interacting, and abundant throughout the universe. They're a dark matter candidate, searched for in dedicated experiments. Discovering axions would confirm instant physics plays a real role in nature. Topological quantum field theories take the field concept to an extreme. These theories have no local degrees of freedom, no propagating particles at all. Yet they describe real physics, particularly in condensed matter systems and quantum computing applications. Topological field theories depend only on global properties of spacetime, not local field values. They classify quantum states by their topological properties, leading to phenomena like anyonic statistics and topologically protected quantum information. The fractional quantum Hall effect exemplifies this physics. Electrons confined to 2 dimensions in strong magnetic fields form exotic states where excitations carry fractional electric charge. These quasi-particles aren't fundamental particles, but collective excitations of the electron field. They obey unusual statistics, neither fermions nor bosons, but anyons. Their behavior can be described by topological quantum field theory, revealing deep connections between quantum field theory and topology. Conformal field theories represent another special class. These theories possess scale invariance. Physics looks the same at all distant scales. In 2 spacetime dimensions, conformal symmetry is infinite dimensional, making these theories highly constrained and often exactly solvable. They describe critical points of phase transitions, string theory on certain backgrounds, and the ADS/CFT correspondence connecting gravity to quantum field theory. ADS/CFT correspondence, discovered by Juan Maldacena in 1997, might be the most important development in theoretical physics since the Standard Model. It states that certain quantum field theories without gravity are exactly equivalent to string theories that include gravity, living in a higher dimensional spacetime. A conformal field theory in 4 dimensions corresponds to string theory in 5-dimensional anti-de Sitter space. The 2 descriptions are different languages for the same physics. This duality has profound implications. It provides a concrete realization of the holographic principle, the idea that physics in a volume of space can be encoded on its boundary. It offers tools for studying strongly coupled quantum field theories by translating them into weakly coupled gravity problems. It suggests that spacetime itself might be emergent, arising from the entanglement structure of quantum fields. Researchers continue exploring these connections, hoping they'll illuminate quantum gravity's nature. Supersymmetry proposes a new kind of symmetry relating fermions and bosons. For every fermion field, supersymmetry predicts a bosonic partner. For every boson field, a fermionic partner. The electron would have a supersymmetric partner called the selectron. The photon would have the photino. These superpartners haven't been discovered, suggesting that if supersymmetry exists in nature, it must be broken at energy scales above what current experiments reach. Why care about an unobserved symmetry? Supersymmetry would solve several standard model problems. It stabilizes the Higgs mass against quantum corrections that would otherwise drive it to enormous values. It provides dark matter candidates, the lightest supersymmetric particle, would be stable and weakly interacting. It allows the fundamental forces to unify at high energies, suggesting a grand unified theory. And it's required for superstring theory, the most developed approach to quantum gravity. The Large Hadron Collider searched extensively for supersymmetric particles. None appeared. Each null result pushes the possible supersymmetry breaking scale higher, making the theory less attractive. Either supersymmetry is broken at energies beyond LHC's reach, or nature doesn't use this particular symmetry. The question remains open, but enthusiasm has dampened as experimental constraints tighten. Quantum field theory's extraordinary success shouldn't obscure its limitations. It doesn't include gravity. General relativity describes space-time curvature, but isn't a quantum field theory. Attempts to quantize gravity using standard field theory techniques fail. The theory isn't renormalizable, producing infinities that can't be absorbed into redefinitions of physical parameters. This suggests quantum gravity requires fundamentally new principles beyond quantum field theory as currently formulated. String theory attempts to provide that framework. Instead of point particles, fundamental objects are one-dimensional strings. Different vibration modes of these strings correspond to different particles. Gravitons emerge naturally as one vibration mode. The theory is finite. No ultraviolet divergences plague calculations. But string theory requires extra spatial dimensions, introduces vast numbers of possible vacuum states, and makes predictions at energies far beyond experimental reach. Whether it's the correct path toward quantum gravity remains uncertain. Loop quantum gravity takes a different approach, attempting to quantize spacetime's geometry directly. Space becomes discrete at Planck scale, composed of finite loops and networks. This eliminates infinities, but introduces new conceptual challenges. How does continuous spacetime emerge from discrete structure? Can loop quantum gravity reproduce general relativity's predictions at large scales? The program continues developing, offering an alternative to string theory's extra dimensions and fundamental strings. Quantum field theory stands as one of humanity's greatest intellectual achievements. It describes matter and forces with precision unmatched in any other science. Yet it points beyond itself toward unknown physics. Dark matter, dark energy, neutrino masses, matter-antimatter asymmetry, quantum gravity. Each mystery hints that deeper principles await discovery. The fields that gave us the standard model might be approximations to something stranger still. Beyond those theoretical frontiers lies experimental reality. The Large Hadron Collider represents humanity's most ambitious attempt to probe quantum fields directly. This underground ring, 17 miles around, accelerates protons to energies never before achieved in controlled conditions. When protons collide at nearly light speed, their kinetic energy converts into excitations of various quantum fields, creating particles that existed only in the universe's first moments. Each collision produces a spray of particles recorded by massive detectors. Engineers built these instruments with exquisite precision. Millions of sensors track particles' paths, energies, and decay patterns. Computer systems process petabytes of data, searching for signatures of new physics. Most collisions produce familiar particles, electrons, muons, quarks combining into hadrons. Occasionally, something rare appears. The Higgs boson discovery exemplified this process. Physicists predicted its existence decades earlier. The particle should appear when enough energy excites the Higgs field above its non-zero vacuum value. But creating that excitation requires tremendous energy. The Higgs mass is about 125 times a proton's mass. The LHC achieved sufficient collision energies in 2010. Then came the waiting. Higgs bosons, once created, decay almost instantly into other particles. Physicists couldn't observe the Higgs directly. They looked for decay signatures, specific combinations of particles appearing with characteristic energies and rates. Among billions of collisions, they searched for subtle statistical excess, events that happen slightly more often than background processes alone would predict. By 2012, the signal emerged. Both major LHC detectors, ATLAS and CMS, saw the same pattern independently. A new particle appeared at 125 gigaelectronvolt mass, decaying into photon pairs, Z-boson pairs, and other predicted channels. The discovery confirmed the Higgs field's existence and validated the mechanism giving particles mass. That achievement earned Higgs and Englert the Nobel Prize, but it also marked a beginning rather than an ending. Because the Higgs boson's measured properties raise new questions. Its mass sits in a peculiar range, heavy enough to require enormous energy for creation, yet light enough to be unstable against quantum corrections. In quantum field theory, virtual particles constantly pop in and out of existence. These fluctuations should contribute to the Higgs mass through loop diagrams, where virtual particles briefly appear before annihilating. Calculating these contributions gives absurd results. The Higgs mass should be driven to enormous values, roughly the Planck scale where quantum gravity becomes important. That's about 10 to the power of 16 times heavier than observed. Something must be cancelling these huge quantum corrections with extraordinary precision. Physicists call this the hierarchy problem. Supersymmetry would solve it elegantly. Remember that hypothetical symmetry relating fermions and bosons. Virtual fermions and virtual bosons contribute to the Higgs mass with opposite signs. If supersymmetric partners existed with appropriate masses, their contributions would cancel, stabilizing the Higgs mass at observed values. This cancellation would be automatic, arising from supersymmetry's mathematical structure rather than requiring fine-tuned adjustments. The LHC searched extensively for supersymmetric particles. Experiments looked for missing energy signatures, supersymmetric particles escaping detectors unobserved. They searched for new heavy particles decaying into familiar ones, plus invisible superpartners. They explored countless possible mass combinations and decay channels. Nothing appeared. Each null result constrains where supersymmetry could hide. If it exists, the symmetry must be broken at energies beyond LHC's reach. The lightest supersymmetric particles must be heavier than several hundred gigaelectronvolts, possibly over a teraelectronvolt. These constraints make supersymmetry less attractive as a natural solution to the hierarchy problem. Either the superpartners are heavier than originally hoped, requiring more fine-tuning to stabilize the Higgs mass, or nature doesn't use this particular symmetry. Alternative explanations exist. Perhaps the Higgs isn't fundamental but composite, built from more basic constituents bound by some new strong force. Just as protons are made of quarks, the Higgs might be a bound state of deeper particles. This compositeness could naturally explain its mass scale, but composite Higgs models predict other new particles that haven't appeared either. Or maybe the hierarchy problem isn't actually a problem. The multiverse hypothesis suggests countless universes with different physical constants. In most, the Higgs mass might indeed be enormous, making chemistry and life impossible. We necessarily observe a universe where the Higgs mass allows our existence, an anthropic selection effect, rather than a fundamental explanation. This reasoning disturbs many physicists who prefer explanations based on natural mechanisms, rather than observer selection. Dark matter adds another layer of mystery. Astronomical observations provide overwhelming evidence for its existence. Galaxies rotate too fast to be held together by visible matter alone. Galaxy clusters contain more mass than their stars and gas account for. Gravitational lensing reveals invisible mass-bending light from distant objects. The cosmic microwave background's temperature fluctuations encode dark matter's influence on early universe structure. Yet we don't know what dark matter is. It must be electrically neutral, otherwise it would interact with light and wouldn't be dark. It must be stable, persisting since the early universe. It must be cold, meaning non-relativistic during galaxy formation. These constraints suggest a new particle, something beyond the standard model. Weakly interacting massive particles were the leading candidate for decades. These hypothetical particles would interact through gravity and possibly the weak nuclear force, but not electromagnetism or the strong force. WIMPs would have been created in the hot early universe, surviving to the present as relic abundance. Their predicted density matches observed dark matter density for certain mass ranges, a remarkable coincidence called the WIMP miracle. Experimental searches looked for WIMPs scattering off atomic nuclei in underground detectors. Shielded from cosmic rays deep beneath mountains, these experiments waited for dark matter particles from the galactic halo to occasionally strike detector atoms. The recoiling nucleus would produce light or charge signals indicating collision. Years passed. Detectors grew more sensitive, capable of detecting ever smaller energy deposits. The experiments reached sensitivities where standard WIMP models predicted observable signals. Nothing appeared. The null results don't definitively rule out WIMPs. Dark matter might interact more weakly than hoped, or have masses outside searched ranges. But the simplest WIMP scenarios are increasingly constrained. Axions offer a different possibility. These ultralight particles were originally proposed to solve a problem in quantum chromodynamics, why the strong force doesn't violate certain symmetries it could in principle violate. Axions would be much lighter than WIMPs, potentially billions of times lighter than electrons. They would behave more like waves than particles, filling the galaxy with a quantum field oscillating at characteristic frequencies. Experiments search for axions by looking for their conversion into photons in strong magnetic fields. The setup resembles a radio receiver tuned to unknown frequencies. Researchers slowly scan through possible axion masses, looking for faint signals. Some experiments have reached sensitivities where certain axion models predict detection. The searches continue, exploring broader mass ranges with increasing precision. Other candidates exist. Sterile neutrinos, hypothetical heavy neutrinos that don't interact through weak force, could comprise dark matter. Primordial black holes formed in the early universe might account for some fraction. More exotic possibilities include mirror matter, dark photons, or particles from extra dimensions. The space of theoretical possibilities remains vast. Whatever dark matter is, its nature connects to quantum field theory's deepest questions. If it's a new particle, it requires extending the standard model. That extension must explain why dark matter is stable, why it has the observed abundance, and how it was produced in the early universe. These requirements constrain possible theories, but many options remain viable. Neutrino masses present another standard model extension that's been experimentally confirmed. The original standard model predicted massless neutrinos. Experiments proved otherwise. Neutrino oscillations, where neutrinos change flavor as they propagate, require that neutrinos have mass and that different neutrino types have different masses. These oscillations manifest in fascinating ways. Solar neutrinos are produced in the sun's core through fusion reactions. By the time they reach Earth, about 2/3 have transformed into other neutrino flavors our detectors can't see. Atmospheric neutrinos created by cosmic rays striking the atmosphere also oscillate, with upward traveling neutrinos showing different flavor composition than downward traveling ones because they travel different distances. Adding neutrino masses to the standard model seems straightforward. Just include mass terms in the theory, but the implementation raises deep questions. Neutrinos might be Dirac fermions, like electrons, with distinct particles and antiparticles, or they might be Majorana fermions, identical to their own antiparticles. This distinction has profound implications. If neutrinos are Majorana particles, their masses arise through a different mechanism than other fermions. The seesaw mechanism provides one explanation. Suppose heavy right-handed neutrinos exist with masses near the grand unification scale. These heavy neutrinos could naturally generate tiny masses for ordinary neutrinos through quantum corrections. The observed neutrino masses are inversely related to the heavy neutrino masses, hence the seesaw name. This mechanism connects neutrino masses to physics at extraordinarily high energies, far beyond anything colliders can directly probe. It might explain why neutrinos are so much lighter than other fermions, and it could account for the universe's matter-antimatter asymmetry through a process called leptogenesis. When heavy neutrinos decayed in the early universe, they might have produced slightly more leptons than antileptons, eventually generating the matter excess we observe. Testing these ideas requires extraordinary experiments. Double beta decay searches look for rare nuclear processes where two neutrons simultaneously transform into protons, emitting two electrons. If neutrinos are Majorana particles, a neutrinoless version of this decay should occasionally occur. The two neutrinos annihilate before leaving the nucleus. Observing this process would prove neutrinos are Majorana fermions and measure their absolute masses. Experiments use hundreds of kilograms of special isotopes, waiting years for events that might never occur. The detectors sit deep underground, shielded from cosmic rays that could mimic the signal. After decades of searching, no confirmed neutrinoless double beta decay has been observed. The experiments continue with increasing sensitivity, exploring parameter space where theoretical models make predictions. Cosmic rays probe energies beyond any collider. When ultra-high energy cosmic rays strike the atmosphere, they create particle showers cascading through the air. Some cosmic rays carry energies exceeding 10 to the 20 electron volts, a single atomic nucleus carrying roughly the kinetic energy of a thrown baseball. How nature accelerates particles to these energies remains mysterious. The Pierre Auger Observatory studies these events using detectors spread across thousands of square kilometers. Water tanks record shower particles reaching the ground. Fluorescence detectors observe ultraviolet light emitted by nitrogen excited in the shower. Together, These measurements reconstruct the primary particle's energy and arrival direction. The highest energy cosmic rays seem to come from random directions rather than pointing to specific sources. This randomness might result from magnetic fields in our galaxy deflecting charged particles. Or perhaps the sources are distant, beyond the range where particles maintain correlation with their origin. The cosmic ray energy spectrum shows features, the knee, the ankle, possible cutoffs that constrain production mechanisms. When cosmic rays interact in the atmosphere, they produce neutrinos. These neutrinos can traverse Earth, entering detectors from below. The ice cube experiment embedded thousands of sensors in Antarctic ice, creating a cubic kilometer neutrino detector. When high-energy neutrinos occasionally interact in the ice, they produce charged particles that emit Cherenkov radiation, a shockwave of light analogous to a sonic boom. IceCube detects this light, reconstructing neutrino energies and directions. Some detected neutrinos come from distant astrophysical sources, blazars, supernovae remnants, possibly dark matter annihilation. Each neutrino carries information about violent processes in its source. Unlike photons, neutrinos travel undeflected by magnetic fields and unabsorbed by intervening matter. They provide a unique window into extreme environments. Gravitational waves opened another window recently. LIGO detected space-time ripples from merging black holes in 2015, confirming a century-old prediction and inaugurating gravitational wave astronomy. These observations don't directly probe quantum fields. Gravitational waves are described by classical general relativity, but they reveal phenomena where quantum field theory in curved spacetime becomes relevant. When black holes merge, enormous energies concentrate in small regions. Virtual particles near the event horizon experience extreme tidal forces. Hawking radiation, a quantum effect where virtual particle pairs separate at the horizon, allowing one to escape, should occur around all black holes. Detecting this radiation remains beyond current technology for stellar mass black holes, but it represents a genuine prediction where quantum field theory meets gravity. The tension between quantum field theory and general relativity grows acute in extreme conditions. Inside black holes, space-time curvature becomes infinite at the singularity. Quantum field theory assumes a smooth background space-time. When that background develops singularities, the theory breaks down. Similarly, in the universe's first moments, all matter and energy occupied an infinitesimal volume. Classical general relativity predicts a singularity at the Big Bang. Quantum effects must have been crucial, but we lack a complete quantum theory of gravity to describe them. String theory attempts that unification. Instead of point particles, it proposes one-dimensional strings as fundamental objects. Different vibration modes correspond to different particles. One mode produces gravitons, quantized gravitational waves. The theory naturally includes gravity alongside other forces, potentially resolving the incompatibility between quantum mechanics and general relativity. But string theory requires extra spatial dimensions beyond the familiar three. These dimensions must be compactified, curled up at scales too small to observe directly. The compactification geometry determines what physics emerges at low energies. Unfortunately, the theory allows vast numbers of possible geometries, perhaps 10 to the power of 500 different vacuum states. Each corresponds to a universe with different physical constants. Without knowing which vacuum describes our universe, string theory struggles to make testable predictions. Loop quantum gravity takes a different approach, quantizing space-time geometry directly. Space becomes discrete at the Planck scale, smallest meaningful length. Smooth space-time emerges from underlying quantum geometry, like water appearing smooth despite being made of molecules. This discreteness eliminates certain infinities plaguing other quantum gravity approaches. The theory makes predictions about the very early universe and black hole interiors. It suggests the Big Bang singularity might be replaced by a bounce, where the universe contracts to Planck density, then rebounds into expansion. Inside black holes, quantum geometry effects might prevent true singularities from forming. Testing these predictions requires observations of the early universe or black hole physics that remain challenging. Both string theory and loop quantum gravity remain works in progress. Neither has achieved the same level of experimental confirmation as quantum field theory. They represent our best current attempts to extend physics beyond the standard model into regimes where both quantum mechanics and gravity matter. The ultimate theory might incorporate elements of both, or might be something entirely different we haven't imagined yet. What we know with certainty is that quantum field theory, despite its extraordinary success, points beyond itself. Every unsolved mystery, dark matter, neutrino masses, matter-antimatter asymmetry, quantum gravity, suggests new physics waiting for discovery. The fields that gave us the standard model are likely approximations to some deeper structure. Our current understanding, as complete as it seems within its domain, forms just one chapter in an ongoing story. Yet quantum field theory extends beyond even these ambitious unification attempts. Every experiment revealing new phenomena, neutrino oscillations, dark matter effects, cosmic inflation signatures, points toward physics that transcends our current framework while building upon it. Consider neutrinos. The standard model originally treated these particles as massless. Then experiments detected neutrino oscillations, neutrinos changing flavor as they travel. One neutrino type transforms into another, electron neutrinos becoming muon neutrinos. This transformation only makes sense if neutrinos have mass, and if different neutrino types have different masses. The discovery forced modifications to the standard model. Physicists added terms allowing neutrino masses, but the origin of these masses remains mysterious. Unlike other particles that acquire mass through Higgs field interactions, neutrinos might get mass through a completely different mechanism. The leading candidate, the seesaw mechanism, involves new particles at energy scales far beyond current collider capabilities. Neutrino masses also raise profound questions about symmetry. All other fermions in the standard model are left-handed or right-handed versions of the same particle. Neutrinos appear only in left-handed form. Right-handed neutrinos, if they exist, interact so weakly with other matter that detecting them might be impossible. These hypothetical particles could be their own antiparticles, unlike any other known fermion. This property connects to one of the universe's deepest mysteries: why matter dominates over antimatter. The Big Bang should have created equal amounts of both. They should have annihilated almost completely, leaving a universe of pure energy. Yet matter survived. We exist. Galaxies exist. Something broke the symmetry between matter and antimatter in the early universe. Quantum field theory provides mechanisms for this asymmetry. Certain particle interactions violate charge parity symmetry, treating matter and antimatter slightly differently. These violations, discovered in quark systems and measured precisely, aren't large enough to explain the observed matter excess. Additional sources of symmetry breaking must exist. Right-handed neutrinos, if they exist, and if they decay in specific ways, could generate the matter-antimatter asymmetry. This leptogenesis scenario remains speculative, but demonstrates how quantum field theory connects particle physics to cosmology. The field's governing subatomic interactions might explain the universe's large-scale structure. Dark matter presents another puzzle demanding extension beyond known quantum fields. Astronomical observations, galaxy rotation curves, gravitational lensing, cosmic structure formation all indicate that 85% of the universe's matter is invisible. This dark matter doesn't emit or absorb light. It interacts gravitationally, but apparently not electromagnetically. The standard model contains no dark matter candidate. Every known particle either has the wrong properties or insufficient abundance. This gap requires new fields, new particles beyond our current catalogue. Dozens of proposals exist. Weakly interacting massive particles, WIMPs, would be heavy particles interacting through the weak force. Axions would be ultralight particles introduced to solve a different problem in quantum chromodynamics, but which could also constitute dark matter. Sterile neutrinos would be right-handed neutrinos that mix weakly with ordinary neutrinos. Each possibility corresponds to adding new quantum fields to the theoretical framework. These fields would exist everywhere, like all quantum fields, but their excitations would rarely interact with ordinary matter. Dark matter particles could be passing through you constantly, billions per second, without leaving any trace. Detection experiments pursue multiple strategies. Deep underground detectors watch for rare collisions between dark matter and atomic nuclei. Space telescopes search for signals from dark matter particles annihilating in galaxy centers. Particle colliders attempt to create dark matter in high-energy collisions. So far, no confirmed detection. The null results constrain possibilities, but haven't eliminated the mystery. Dark matter remains, stubbornly refusing to reveal its nature while leaving gravitational fingerprints throughout the cosmos. Inflation, the exponential expansion in the universe's first moments, also connects to quantum fields. This rapid expansion would have stretched quantum fluctuations in some field to cosmic scales. Those fluctuations seeded the density variations that eventually collapsed into galaxies. The cosmic microwave background preserves these primordial fluctuations. Temperature variations across the sky match predictions from quantum fields during inflation remarkably well. But we don't know which field drove inflation. The inflaton field, whatever it was, must have properties allowing brief, intense expansion before decaying into ordinary matter and radiation. Candidates include new scalar fields similar to the Higgs, existing fields playing dual roles, or modifications to gravity itself at high energies. Each proposal makes testable predictions about the pattern of fluctuations, the presence of gravitational waves from inflation, and the universe's geometry. Current observations favor certain inflation models while disfavoring others. Future experiments, more sensitive cosmic microwave background measurements, gravitational wave detectors capable of seeing primordial signals, will further narrow possibilities. Quantum field theory provides the mathematical language for making these predictions precise. Even the vacuum energy problem demonstrates quantum field theory's power and limitations. quantum fluctuations in fields should contribute energy to empty space. Calculating this vacuum energy density gives a result roughly 120 orders of magnitude larger than the observed dark energy density. This cosmological constant problem represents perhaps the worst prediction in physics history. Something must cancel the vacuum energy almost perfectly, leaving only the tiny residual we observe as dark energy. But we don't know what provides this cancellation or why it's so precisely tuned. Proposed solutions range from anthropic arguments. We observe this particular vacuum energy because other values wouldn't allow life, to supersymmetry, which could naturally cancel many vacuum energy contributions. None fully resolves the puzzle. The problem might signal that quantum field theory, while correct for particle physics, needs modification when applied to cosmology. Space-time itself might behave quantum mechanically in ways we haven't incorporated. Gravity's quantum nature could alter vacuum energy calculations fundamentally. These frontiers, neutrino physics, dark matter, inflation, vacuum energy, all suggest that quantum field theory as currently formulated is incomplete. Not wrong within its tested domain, but insufficient for the full story. Experimentalists continue probing for deviations from standard model predictions. The Large Hadron Collider searches for new particles, unexpected decay rates, anomalous interactions. Precision measurements test quantum electrodynamics to ever higher accuracy. Neutrino experiments map oscillation patterns. Dark matter detectors wait patiently for signals. Each measurement either confirms existing theory or hints at something beyond. Small discrepancies appear occasionally. The muon's magnetic moment differs slightly from theoretical predictions. Certain particle decays occur at unexpected rates, but most haven't reached definitive significance. They tantalize without quite delivering revolution. Theorists, meanwhile, explore extensions to the standard model. Supersymmetry doubles the particle count, pairing every fermion with a boson and vice versa. Extra dimensions could hide at scales just beyond current experimental reach. Composite models suggest quarks and leptons aren't fundamental, but made of more basic constituents. Each extension preserves quantum field theory's core structure, while adding new fields, new symmetries, new interaction possibilities. The mathematical framework proving so successful for known particles should apply equally to undiscovered ones. This confidence stems from quantum field theory's remarkable track record. When properly applied within its domain, it makes predictions confirm to extraordinary precision. The electron magnetic moment, calculated through quantum electrodynamics, matches measurement to 12 decimal places. Particle collision rates at accelerators match theoretical predictions across dozens of processes and many orders of magnitude in energy. Such success suggests the fundamental approach, describing nature through quantum fields and their interactions, captures something deep about reality. Even if specific field content changes, even if new particles emerge, the field theoretic framework should survive. The mathematical structure might even point toward unification beyond the standard model. Grand unified theories attempt to merge the strong, weak, and electromagnetic forces into a single interaction at extremely high energies. At low energies, symmetry breaking separates them into the distinct forces we observe. These theories make predictions testable in principle. Protons should eventually decay. Magnetic monopoles should exist. Certain force strengths should converge at high energy. None have been confirmed yet, but experimental limits continue tightening. Whether grand unification proves correct or not, the quest demonstrates how quantum field theory enables concrete predictions about physics at energies far beyond direct experimental access. By understanding how forces change with energy, how coupling constants run, we can extrapolate from measured values to extreme conditions. This extrapolation has limits. Eventually, we reach energies where quantum gravity becomes important. Particle interactions involve energies high enough that their gravitational fields become quantum mechanical. The Planck energy, about 10 to the power of 19 giga-electronvolts, represents this scale. At Planck energies, space-time itself fluctuates quantum mechanically. The smooth geometry assumed in quantum field theory breaks down. We need a quantum theory of gravity, merging general relativity's curved space-time with quantum mechanics' uncertainty and superposition. String theory and loop quantum gravity attempt this merger from different directions. Neither has achieved quantum field theory's level of experimental confirmation. They remain frameworks under development, producing interesting mathematics, but few testable predictions. Yet they build on quantum field theory's insights. String theory contains quantum fields as low-energy approximations to string dynamics. Loop quantum gravity quantizes space-time geometry using techniques developed for quantum fields. Both preserve the lesson that fields, not particles, are fundamental. Future experiments will continue testing quantum field theory while searching for its boundaries. Higher energy collisions, more precise measurements, astronomical observations spanning cosmic history, all probe whether reality truly conforms to field-theoretic descriptions or whether surprises await. The questions multiply as measurements improve. Why do particles have the masses they do? Why 3 generations of fermions? Why these particular force strengths? Could physical constants vary across space or time? Does quantum field theory remain valid at arbitrarily high energies, or does something new emerge? These questions drive experimental programs worldwide. Particle colliders push toward higher energies. Precision experiments measure properties to unprecedented accuracy. Cosmological observations map the universe's evolution and composition. Each measurement either confirms current understanding or reveals anomalies demanding explanation. The interplay between theory and experiment continues. Theoretical predictions guide experimental design. Experimental results validate or challenge theories. Successful theories inspire new experiments. Unexpected observations spark theoretical innovation. This dialogue has driven physics for centuries. Quantum field theory represents our current best answer for matter and forces at fundamental scales. Like all scientific theories, it remains provisional, subject to modification or replacement if evidence demands. But that evidence must be compelling. Extraordinary claims require extraordinary proof. Any replacement for quantum field theory must reproduce its successes while explaining what it cannot. Until then, quantum field theory stands as our deepest understanding of matter and forces. Its successes aren't modest achievements, they're among the most precise predictions in all of science. When theorists calculate how an electron responds to a magnetic field using quantum field theory, the prediction matches measurement to 12 decimal places. Imagine predicting the distance from New York to Los Angeles and being accurate to within the width of a human hair. That's the precision quantum field theory delivers. But precision alone doesn't capture what makes this framework revolutionary. Quantum field theory fundamentally reimagines what exists. Before this framework emerged, physicists thought of particles as primary objects, tiny billiard balls bouncing through empty space. The electromagnetic field was merely the influence one charged particle exerted on another across distance. Quantum field theory inverts this picture completely. Fields are primary. Particles are secondary manifestations, temporary excitations in underlying fields that permeate all of space. This inversion solves puzzles that seemed intractable in earlier frameworks. How can particles be created and destroyed? In a particle-centric view, creation and destruction seem mysterious, almost magical. But if particles are excitations in fields, creation and destruction become natural. Adding energy to a field creates an excitation. Removing energy makes the excitation vanish. No mystery required. The field itself continues existing whether excited or not. Consider what happens when matter meets antimatter. An electron encounters a positron. They annihilate, producing photons. In the field picture, excitations in the electron and positron fields disappear, while excitations in the electromagnetic field appear. Energy and momentum are conserved. The process follows definite mathematical rules. Quantum field theory calculates the probability of this occurring, predicts the photon energies and directions, matches experimental observations perfectly. Or consider nuclear fusion inside stars. Protons overcome electromagnetic repulsion and fuse, releasing energy. Quantum field theory describes this through quark field interactions mediated by gluon fields. The strong nuclear force emerges from the mathematical structure of these fields and their symmetries. Calculations predict fusion rates, energy release, the types of particles produced. These predictions guide our understanding of stellar evolution, explain how stars shine for billions of years, account for the creation of heavier elements through successive fusion reactions. Every chemical bond holding molecules together, every electrical current flowing through wires, every light wave traveling from the sun, all emerge from quantum field dynamics. The electromagnetic field mediates every chemical reaction. Electron fields determine molecular structure. Photon fields carry electromagnetic radiation. Nothing in chemistry, biology, or everyday physics escapes quantum field theory's reach. The framework isn't some abstract mathematical game divorced from reality. It's the foundation upon which observable reality rests, yet mysteries persist. Dark matter comprises roughly 85% of the universe's mass, but doesn't fit the standard model. No known particle field produces dark matter's gravitational effects without interacting electromagnetically. Either additional fields exist beyond those we've discovered, or our understanding of gravity requires modification. Experiments worldwide search for dark matter particles, hypothetical excitations in unknown fields. Detectors buried deep underground watch for rare interactions. Particle colliders attempt creating dark matter through high-energy collisions. So far, nothing definitive has emerged. Dark energy presents an even deeper puzzle. This mysterious component drives the universe's accelerating expansion, comprising about 70% of total cosmic energy. Is dark energy a field? If so, it behaves unlike any field in the standard model. Its energy density remains constant even as space expands, violating our usual understanding of how fields work. Or perhaps dark energy isn't a field at all. but rather a property of space-time itself. Einstein's cosmological constant resurrected. Current observations can't definitively distinguish between these possibilities. Neutrinos add their own complications. These particles interact so weakly they can pass through light years of solid matter without being stopped. The Standard Model originally assumed neutrinos were massless, but experiments prove they have tiny masses and can oscillate between types. This requires adding new terms to the theory, possibly introducing new fields. The exact mechanism giving neutrinos mass remains uncertain. Does the Higgs field interact with neutrinos, or do additional fields exist? And why are neutrino masses so much smaller than other particle masses? No compelling explanation has emerged. The matter-antimatter asymmetry poses another fundamental question. The Big Bang should have created equal amounts of matter and antimatter. When they met, they should have annihilated, leaving a universe filled with photons, but no atoms, no stars, no galaxies, no us. Yet matter dominates the observable universe. Antimatter exists only briefly in cosmic rays and particle accelerators. The Standard Model contains mechanisms for slight matter-antimatter differences, but calculations show these can't explain the observed asymmetry. Something beyond current understanding must have tipped the balance. Gravity's absence from quantum field theory represents perhaps the most glaring gap. General relativity describes gravity as space-time curvature caused by mass and energy. This works brilliantly at large scales, predicting black holes, gravitational waves, the universe's expansion. But general relativity isn't a quantum theory. It treats space-time as smooth and continuous, ignoring quantum fluctuations. At small scales and high energies, quantum effects become crucial. Space-time itself should fluctuate quantum mechanically. We need a quantum theory of gravity. Attempts to build such a theory face severe obstacles. Standard quantum field theory techniques applied to gravity produce non-renormalizable infinities. Unlike the infinities in quantum electrodynamics that can be systematically removed, gravity's infinities proliferate uncontrollably. Each attempt to remove them introduces new infinities. The theory becomes unpredictable, useless for making calculations. This suggests quantum field theory as currently formulated can't describe gravity. Either new mathematical techniques are needed, or gravity requires a fundamentally different framework. String theory offers one possibility. Instead of point particles being field excitations, perhaps fundamental objects are tiny vibrating strings. Different vibration modes correspond to different particles. Gravity emerges naturally as one vibration mode. String theory appears mathematically consistent, avoiding the infinities plaguing quantum gravity. But string theory requires extra spatial dimensions beyond the three we observe. These extra dimensions must be curled up small enough to escape detection. The theory makes few testable predictions at accessible energies. After decades of development, no experimental evidence confirms strings exist. Loop quantum gravity takes a different approach, attempting to quantize space-time itself. Space becomes granular at the Planck scale, composed of discrete quantum units rather than being infinitely divisible. General relativity emerges as a low-energy approximation to this more fundamental quantum geometry. Loop quantum gravity makes specific predictions about space-time structure at tiny scales. But like string theory, these predictions involve energies far beyond current experimental reach. Neither framework has achieved quantum field theory's level of experimental confirmation, Perhaps the lesson is humility. Quantum field theory works spectacularly well within its domain, describing particles and forces at energies we can access experimentally. But it may not be the final answer. Just as Newtonian mechanics works perfectly for everyday phenomena, but required replacement by relativity and quantum mechanics for extreme conditions, quantum field theory might need embedding in a deeper framework. That framework should reproduce quantum field theory's successes while extending beyond its limitations. What would such a framework look like? We don't know. History suggests the answer will surprise us. When quantum mechanics emerged, it violated every intuition about how reality should behave. Particles existing in multiple states simultaneously, measurements affecting what's measured, probability replacing determinism. These seemed absurd until experiments forced their acceptance. Special relativity's claim that time passes differently for different observers contradicted common sense. General relativity's curved space-time seemed like mathematical abstraction until gravitational waves were detected. Each revolutionary theory shocked the physicists who developed it. The next revolution might shock us similarly. Perhaps space-time emerges from something more fundamental. Perhaps information is the universe's primary constituent, with fields and particles being information patterns. Perhaps consciousness plays a role we haven't recognized. Or perhaps reality involves concepts we haven't yet imagined, ideas requiring new mathematics, new language, new ways of thinking about existence itself. But speculation must be grounded. Physics advances through the dialogue between theory and experiment. Theories suggest experiments. Experiments test theories. Successful theories survive. Failed theories get modified or discarded. This process has driven progress for centuries. It will continue driving progress toward whatever lies beyond quantum field theory. Current experiments push multiple frontiers. The Large Hadron Collider searches for new particles at higher energies. Precision measurements test standard model predictions to unprecedented accuracy. Neutrino detectors map oscillation patterns. Dark matter experiments watch for unknown particles. Gravitational wave observatories monitor space-time ripples. Cosmological surveys map the universe's structure and evolution. Each measurement either confirms current understanding or reveals anomalies demanding explanation. Anomalies are where breakthroughs hide. Every major physics revolution began with small discrepancies between theory and experiment. The ultraviolet catastrophe, classical physics predicting infinite energy from hot objects, led to quantum mechanics. The null result of the Michelson-Morley experiment led to special relativity. Anomalous perihelion precession of Mercury led to general relativity. Today's anomalies might herald tomorrow's revolution. Some current anomalies hint at new physics. Muon magnetic moment measurements show slight deviations from standard model predictions. B-meson decays exhibit unexpected patterns. The universe's expansion rate measured different ways gives inconsistent results. Any of these could be experimental error, statistical fluctuation, or misunderstood systematics. Or any could signal physics beyond the standard model. More data will tell. Meanwhile, theoretical work continues exploring possibilities. Supersymmetry proposes each standard model particle has a superpartner with different spin. These superpartners might comprise dark matter. Extra dimensions might exist beyond the four we observe. The vacuum might be metastable, capable of decaying to a lower energy state. the universe might be one of countless universes in a vast multiverse. Some ideas seem outlandish, but physics history shows reality often exceeds imagination. Quantum field theory itself seemed outlandish when first proposed. Virtual particles borrowing energy from nothing, fields filling all space with infinite zero-point energy, particles being excitations in mathematical abstractions. These ideas violated intuition about how nature should work. Yet experiments confirmed them repeatedly. Nature doesn't care about our intuitions. It follows mathematical patterns whether we find them sensible or not. Those patterns possess remarkable beauty. The standard model's structure emerges from symmetry principles. Gauge invariance dictates interaction forms. Symmetry breaking explains mass generation. Conservation laws follow from space-time symmetries. Mathematical elegance guides theoretical development. Physicists trust beautiful theories partly because beauty has proven reliable. The most successful theories often possess the deepest mathematical harmony. But beauty alone proves nothing. Elegant theories disconnected from experiment are mathematics, not physics. Physics requires testability. Predictions must be falsifiable. Experiments must be reproducible. These requirements separate physics from philosophy or pure mathematics. They ensure physics describes reality rather than merely describing our preferences about how reality should be. Quantum field theory meets these requirements triumphantly. Its predictions are tested constantly in laboratories worldwide. Every particle accelerator collision tests quantum chromodynamics. Every atomic transition tests quantum electrodynamics. Every nuclear decay tests electroweak theory. Billions of events measured, billions of predictions confirmed. This sustained experimental success establishes quantum field theory as genuine knowledge about nature. That knowledge enables technology. Quantum field theory underlies semiconductor physics, laser operation, nuclear energy, medical imaging, particle therapy for cancer. Understanding how fields interact lets us manipulate them for practical purposes. The computer or phone displaying these words relies on quantum field effects in its transistors. LED lights use quantum field principles to convert electricity into photons efficiently. PET scanners detect positron annihilation, matter-antimatter destruction predicted by quantum field theory. Knowledge translates into capability. Future technologies might exploit quantum field theory even more directly. Quantum computers use superposition and entanglement, quantum field phenomena, to process information in fundamentally new ways. Quantum communication promises perfectly secure information transmission. Quantum sensors might detect gravitational waves too subtle for current instruments. As understanding deepens, applications multiply. Yet some questions transcend current frameworks entirely. Why do these particular fields exist? Why these symmetries? Why 3 generations of fermions? Why these specific mass values? Quantum field theory describes how fields behave but doesn't explain why these fields exist rather than others. The theory contains roughly 20 free parameters, whose values must be measured experimentally. A deeper theory might predict these values from more fundamental principles, or perhaps no deeper theory exists. Maybe the parameters are environmental, varying across different regions of a multiverse. We observe these particular values because only these values permit complex structures like stars, planets, and observers. Universes with different parameters might exist, but lack anyone to observe them. This anthropic reasoning troubles many physicists, but can't be dismissed without evidence. The questions multiply rather than diminish as knowledge grows. Each answer reveals new mysteries. Understanding quantum fields raises questions about quantum field origins. Explaining the Standard Model's structure prompts questions about why this structure, rather than alternatives. Discovering the Higgs mechanism leads to questions about the Higgs field's properties. Knowledge expands the boundary between known and unknown, increasing the perimeter where mystery resides. That expanding boundary drives science forward. Questions motivate research. Mysteries inspire investigation. The unknown calls to curious minds. As long as questions remain unanswered, physics will continue advancing, pushing toward deeper understanding, broader frameworks, more complete descriptions of reality. Quantum field theory represents our current position in that ongoing journey. Not the destination, but a waypoint, a remarkable achievement, revealing both how far we've come and how far we have yet to travel. The framework that seemed radical a century ago now forms the foundation for exploring what lies beyond. Fields permeate space. Particles are excitations. Forces emerge from symmetries. These insights will persist even as new discoveries extend or modify the framework. So when you observe light, feel solid matter, or contemplate the stars, remember you're experiencing quantum field manifestations. Photons exciting your retina are electromagnetic field quanta. Electrons in your neurons are electron field excitations. Atomic nuclei binding matter together involve quark and gluon fields. Every phenomenon, every interaction, every observable effect emerges from fields permeating reality's deepest level. Those fields continue their quantum dance, whether observed or not. Virtual particles fluctuate in empty space. Vacuum energy fills the cosmos. Fields interact through symmetries discovered and symmetries yet unknown. The universe computes its next state from quantum field dynamics, processing reality at the Planck scale, unfolding existence according to mathematical laws we're still learning to read. The story of quantum fields is ultimately a story about discovery itself, about how profoundly our understanding of reality can shift when we dare to question our deepest assumptions. A century ago, physicists believed particles were fundamental. They imagined tiny, indivisible objects bouncing through empty void. That picture seemed solid, intuitive, grounded in everyday experience. Then experiments forced a revolution. The mathematics demanded fields. Virtual particles appeared in calculations and left measurable traces. Symmetries dictated interactions. What seemed like empty space revealed itself as a seething quantum foam. Reality's foundation shifted from particles to fields, from objects to patterns, from matter to excitations in invisible mathematical entities permeating all existence. This shift continues reshaping physics. Every new measurement either confirms quantum field theory's extraordinary precision or hints at extensions beyond current understanding. Dark matter, neutrino masses, matter-antimatter asymmetry, quantum gravity. Each mystery points toward physics we haven't yet grasped. The Standard Model, for all its success, remains incomplete. Additional fields likely exist. New symmetries might govern interactions at higher energies.